Okay. Hello, everybody. Today we will not be taking the test because of an unfortunate IT error. I do have the test made. I can tell you that tomorrow we will be taking it. It will be 35 questions. You will have the whole class period to finish it, so that's 45 minutes. Same thing with the online folks. If you're watching this video, you can take it anytime tomorrow. Y'all will take it in class, but you will only have 45 minutes to complete it. So make sure that you're ready to go. It will be open book, open notes. And I guess y'all can use the computer because the online people will be using the computer too. Because there's no lockdown browser. Although I encourage you not to, and to see how much you know. I don't think it's too hard of a test. If you've been listening during the lectures, you should probably get most of the questions right. I did throw one or two in there that might make you think, but you could probably logically get to the answer. Maybe, I don't know. Sometimes I think the tests are easy, and then y'all take them, and like, no, that was actually pretty hard. So sometimes it's hard for me to judge how easy or hard a test is. But we will be taking it tomorrow. I was going to wait for the lockdown browser to happen, but it could be a week or more before Stephen Michael gets back. So I don't expect the fill-in people that are coming today and this week to be able to complete that task. Maybe they will. Who knows? Maybe I should have confidence in people, but I generally don't. Today we are going to get into minerals. Let's see if I can move the slides back a little bit here. Yeah. Back to the beginning. So we finished chapter 15 and 16, which are the space chapters. And now we'll go back to the very beginning of the book and start with chapter 1, matter and minerals. And so we're going to start small and work our way big. I will tell you, maybe not for me, but for y'all, this might be one of the most boring chapters in the book. And so I encourage you to muster all you can to be interested in this and pay attention to it. The rock stuff will get more interesting because we do more with rocks. And once we get out of rocks and we get into earthquakes and volcanoes and water movement, although y'all might not find water too interesting, there are some really cool things with it. There's a lot of interesting things to go through in the semester. Minerals kind of takes the right person just to be really into minerals. Even if you have gone out and found different minerals and rocks just for fun on vacation, or if you happen to search the creeks, there's a lot of cool stuff, but I understand that it can be boring, especially this lecture here. But we've got to go through it. This is a good place to start for the entire year. I do like to go through the space stuff first. And so now that we're done with it, we're going to come back to matter and minerals. And we're starting small, and we're going to build our way bigger till we essentially have talked about the entire planet. And so we're starting at literally the atom level, the molecular level. And then we're going to move up to minerals. The next 2 chapters, I believe, will be about rocks. Chapter 2 and 3, I think, are about rocks. And so after that, we'll kind of move into more bigger picture stuff, earthquakes, volcanoes, plate tectonics, big worldwide things. But today, we start small with minerals. They asked the question, what are the defining characteristics of a mineral? It will take us quite a while to answer this. It goes through most of the chapter before this entire question gets answered. But I will start here with this picture. This is a cave. You can see that it's a cave. You can see that there are giant crystals in it. And so someone went really far out on a limb here, and they named this Crystal Cave. Very unique. They put a lot of thought into it. It took them a long time. But in truth, it's just stop being so sarcastic. This is a really cool place. There's almost no other place on Earth that's like this. If there is, I have not seen any pictures of it. You can notice there's a person here. And so these crystals are gigantic. The size of these are kind of unmatched anywhere else in the world. You notice the person's not wearing Bermuda shorts and a Hawaiian shirt. They have I don't know what you would call it. It's a lot of PPE is what they have on, because the gas in here is poisonous. The temperature is extremely hot. I don't know the temperature. If anybody wants to Google it and get some stats on the temperature of the Crystal Cave, it's just called Crystal Cave in Mexico. But yeah, it's very hot in here. 113 degrees inside. I think for safety reasons, the people can only stay in for maybe about an hour, maybe a little bit less more. Humidity is close to 100%, which makes sense. It helps the crystals kind of grow. They're not growing anymore right now. But I'll just start off by saying these minerals grew in a water solution. Almost all caves at some point in time, not almost all of them, all of them. All caves at some point in time were filled with water. It's the water that actually created the cave. The water dissolves the rock around it away. And in this case, it leaves crystals behind because as it was dissolving the rock away, it got filled up with a lot of quartz ions, SiO2, which we'll get to in a second. And as it passes through, these ions start to stick to the walls. And then as they build up and stick to each other more and more and more, you get these crystals that come out. So these are giant quartz crystals, if you're familiar with quartz at all. So that is kind of the way that caves work. And we'll get to that later in the water section. We'll talk about some caves and how they dissolve and stuff. These crystals are very large. And when we get to the igneous section, we will kind of make an equivalence between crystal size and the time it took for them to form. And so these are very, very large. This cave was forming these crystals for more than likely thousands of years, if not tens of thousands or hundreds of thousands. They may have an estimate if there's a Wikipedia page or something for it. But it's a really unique place. I don't think you could go in here as a tourist. Possibly you can, but it's way down deep underground in a mine, and you have to put all the PPE on. So I'm pretty sure this is only like scientists only. And probably even only if you work for the company or the country that happens to be running it. So this is pretty cool. And this is just one of the things that you can find that kind of helps make minerals interesting. I'm trying to remember if I said anything else in first period. No, I think we're good here. So we're going to go on to the next page, and we're going to get this sentence, which is very important, and I will say over and over again throughout this chapter and probably the rock chapters too. Minerals are the building blocks of rocks. In the same way that atoms are the building blocks of literally everything, atoms of different elements build your minerals. Minerals of different types build your different rocks. And so before we can talk about rocks, we have to talk about and understand minerals. Minerals are super important for human evolution and technology. I don't mean like physical evolution. I mean like mental and societal evolution. And so we used flint and chert very, very early on for weapons and tools, and obviously to create fire, which was super important for human development. Once we were able to cook our meats and then stop getting sick from them, we were able to intake a lot more calories and do a lot more things other than just try to survive. We were able to build houses and build societies and do very crazy things that we have today. Gold, silver, and copper were obviously mined by Egyptians. Those are very valuable. They were used for tool making. They were used for wealth and trade. And obviously, if the Egyptians were doing it, this should go without saying, the Chinese were probably doing it too. Our history classes, I don't know about y'all's, but mine severely just did not talk about China and things that they did for almost everything. By the time someone else in the world had done it, China had also done. China was very, very out in front of most of the other developments in the world. Bronze was developed by 2200 BC. Does anybody have a guess as to what makes up bronze? Bronze is an alloy between two different metals. Yeah, I think it's going to be copper and nickel. I'm not positive on that, but I think bronze is copper and nickel. We won't talk too much about metal alloys, but there will be some discussion about it. And then mining became common by the Middle Ages. We were like, we find all this really interesting stuff just lying around the ground. It'd be nice if we could get a whole bunch of it and not just have to look for it to find it. And so we decided to start mining some of these things in areas where we knew that they existed. The study of minerals is called mineralogy. You can actually get a degree in mineralogy and be a mineralogist. It's more specific than a general geology degree. The guy I took my mineralogy class from at OU, Dr. London, he was a very big mineralogist. He has a mineral named after him, which you can't do yourself. And generally in science, I've probably said this before, they don't let you name things after yourself. That's it's like no, it's taboo. So he had a student discover a brand new mineral, and they happened to name it after him. His name's Dr. London, so they called it Londonite. And I think it's even nicer because it's like a gem quality mineral. And so at OU, like in a case, they have like a pair of earrings made out of Londonite, which is pretty interesting. Mineralogy is a very specific branch of geology dedicated just to studying minerals. And you will see we're gonna kind of gloss over some of this stuff because for two reasons. A, this is a non-science majors class, and so we're not going to get too in-depth into anything. B, this is not a mineralogy class. If this were a mineralogy class, we would be doing some in-depth study on what makes up a mineral and all the different types of crystal structures. You'd be getting into physics and chemistry and all sorts of stuff. And so this is kind of one of the ways you'll see that geology takes from all the different branches. We use physics, we use chemistry. When we get into rocks, we use different biologies, and even when you get into paleontology, where we study bones in the rock record, you get into biology. So we don't just stick to geology. We kind of use a little bit of everything, which if you're a science person, makes it fun. So what is the definition of a mineral? This does get a little bit dicey. And for these next couple of slides, you're going to kind of see why some people, including myself, sometimes, not all the time, say that geology is not a hard science. There's a lot of subjectiveness to geology, especially when you get into like the looks of minerals and the feels of minerals. We don't use definite terms. We use kind of loose terms that could be argued over, like earthy feel and pearly luster and dull luster. Like what's dull, what's shiny? There's not like a definite line that you can draw between dull and shiny. It's just kind of up to you at the point in time where you're out in the field looking at things. And so these are the definite rules of what is a mineral. You will see that it's difficult to kind of place things into categories. And there's some people that argue, like when we get to the next slide, they're going to ask you if ice is a mineral. If you look that up, you're going to find different websites that are like, no, ice is not a mineral. And people that are like, definitely, yes, it is. And so there's some subjectiveness to this. So what is the definition of a mineral? A, it has to be naturally occurring. It cannot be made in a lab. And along with that, it has to be inorganic. There are a few exceptions to this, but in general, it can't be made from human processes, especially in a lab. It can't be made by an animal in a way. Or if it is, we don't call it a mineral until that animal is done with it, like a shell or like your bones. Not your bones, but usually aquatic bones. They can become part of the mineral record after the animal dies, and they become part of a rock. So it has to be naturally occurring, not synthetic. So an example of this would be diamonds, which are a mineral, versus cubic zirconium or moissanite, which are not minerals. They're made in a lab, which is why they're much, much cheaper on the market. But from a geology perspective, lab-made things don't really have the context. They don't really have the scientific value that naturally occurring things do. It has to be inorganic and it has to be a solid. They will make an argument in a second that mercury is a mineral and maybe the only liquid mineral. I've never heard of anybody refer to mercury as a mineral. It's just not something that we really care about. It exists in liquid form on Earth's surface. And so I would stick to this solid as a hard yes. It needs to be a solid. Mercury is not a mineral. But know that your book may differ. It does need to be inorganic. This is the important part, or one of the most difficult parts to understand, which kind of makes it very important. It has to have an orderly crystalline structure. And what they mean by that, you have to have a definite and repeatable way that the atoms fit together to create your mineral. If it's just like a loose conglomeration of different atoms in different ways, we're not going to call it a mineral. It needs to be orderly. It needs to be able to be repeated, and it needs to be internally down on the molecular level that makes it shape. And so we will kind of see some examples. I'm going to pass around some minerals in a second. And finally, it has to have a definite chemical composition. If you can't write down a chemical formula for what this mineral is, then it's not a mineral. So like quartz, which I believe this is quartz. It's a tiny sample, but it's quartz. This quartz is SiO2. 1 silicon, 2 oxygens. That's what quartz is. It doesn't matter what color it is. Doesn't matter where you find it in the world. If you break it down and figure out its chemical composition, its formula is SiO2. And that every mineral should be able to have a definite chemical composition that we can state and test and show to people. So generally, minerals are inorganic. And see, they're already putting qualifiers in here. They're like, these are the 4 rules. You got to stick to the rules. And then they're like, generally, it could be something else. So things that are going to be organic, some organisms secrete inorganic compounds like calcium carbonate. These are going to be things that in the ocean that make shells. And so like, not really like snails. I mean, snails do make their own shells, but the spiral shells you see on the beach, nautilus shells, anything that doesn't like take something else's shell is pulling that calcium carbonate out of the water column. It passes through its body, it secretes it on the outside, it uses it to make its shell. At the point that it's using it, we're not calling it a mineral. But it's considered a mineral when the animal dies and that shell or possibly internal structure, I'm going to use the word bones for lack of a better term, become part of the rock record. And so once they die and their detritus settles down to the bottom of the ocean and gets incorporated in the rocks, then it becomes a mineral. And so it gets a little iffy. If you have a plant-based rock like coal, that is not going to be a mineral at any point in time. It's just plant material that's been compressed, and so we generally don't consider that a mineral-based rock. It has to be a crystalline solid. Their example down here is mercury occurs naturally as a liquid. I would say that is not generally considered a mineral. I guess technically, if you're doing like a PowerPoint, I guess, but that's not something we really deal with very much. So it's got to be solid. It's got to have this crystalline compound. And this is what they're showing you here. This is halite. Does anybody know what halite is? Normally, what we call it before we eat it.
Table salt.
It's table salt, yes. And if you take table salt and put it underneath a microscope, literally all of the tiny little pieces are going to look like these clear crystal cubes. And this shows you the orderly crystalline structure. Salt is made up of sodium and chloride. It's pretty much 1-to-1, 1 sodium, 1 chlorine. It's an ionic bond, so it's an ionic compound. And the way they fit together, all the little sodium atoms kind of nestle inside the larger chlorine atoms. And pretty much exclusively, we don't make this happen. This is just the way that nature works. They only form cubes. Sometimes the cubes will be elongated. It's not always like a perfect cube. I guess the proper term would be a prismatic rectangle. I think, if I'm wrong on that, I'm sorry. But it's not necessarily always like a dimensionally perfect cube. But this is what they form. And if you take table salt from your home, this is what you're going to see when you put it underneath the microscope. And so I'm going to turn the lights on real quick. I want to pass these around, kind of pass them around all together so you get to see the differences. But what I have here is a quartz crystal. And when you get the quartz crystal, I'd like you to look at it straight on. And you see that it's 6-sided. It's like a hexagon in profile. This is one of the ways quartz can have several different ones. This is one of the most common ways that quartz forms. And you can easily identify quartz because almost nothing else forms these 6-sided prisms like this. And so if you see it has 6 sides, especially if it comes to a point that looks kind of like a pencil, it's going to be quartz. This one right here, I don't know exactly what this is. I maybe should have looked it up, but I don't know if this has a sheet with it. This is going to be a fibrous mineral, and so it kind of has a square look to it. I don't know that that's necessarily how it formed. It could have just been how it broke off. But you can see the lines running the full length of these. This is going to be fibrous, like serpentinite. There's a couple other I can't remember right off the top of my head. But they're just long little fibers that run the entire length, and it almost works like a fiber optic cable. It's obviously not going to be clean and nice, but you have these two here. I have a nice cube of pyrite. Does anybody know what pyrite is? Fool's gold. So it does have that nice gold shine to it. If you've ever seen real gold, fool's gold does not look the same. That's not why they call it like tricky gold or almost gold. You're an idiot if you think this is gold, especially back in the times when people used gold for money and trading and stuff like that. Also, you know the Olympic people, what do they do with their gold medals? They buy them. They pretend to buy them because they're not solid gold. They're just gold plated now, so you'd probably hurt your teeth if you actually bit it. But the reason is gold is soft. Pyrite is not soft. You will hurt your teeth if you try to bite it. It won't leave like teeth marks. And then this is gypsum. Gypsum's the state rock of Oklahoma, and this is not quite, but this is like a gypsum rose. And so it's these like flat little plates, and they kind of all form in a ball. And this one doesn't really look like a rose, but they kind of have a flower kind of look to them, like little petals all in a circle. That one's a little bit chaotic, but that's just a small example of how, depending on what atoms you have, they're literally like building blocks. And so if you have different building blocks, they're only going to be able to connect in certain ways and make certain shapes, which means that your minerals that come out will be limited to those specific shapes. And so y'all pass those around, take a look at them, pick them up, feel them, touch them.
I think you were right about that being
selenite. Yeah, it could. Yeah,
selenite.
Selenite. I said serpentinite, which is also a fibrous one. But yeah, selenite. That's probably what it is. I think that's one of the rocks I just have randomly and not from one of these packs that has a worksheet kind of thing on it. Yes, but don't touch it. It's probably this one. This is yellow, but I don't think it's silver. You can take it out. It's in the bag, but if you touch it, your hands are going to smell like silver all day. Like even if you wash them, it's not going to come off. Yeah. Oh, okay. So as y'all pass those around, just kind of take note of the different shapes, the different colors, and note that those are really good examples of their representative minerals. Before you leave out of class, you can kind of come take a look at these. Maybe don't pick them up too much because I like to keep them in order. But we have a lot of samples in here that aren't representative samples. And I had a teacher that used to do that to us. He would show us all the nice, like perfect, wonderful samples. He'd be like, this is what salt looks like. This is what quartz looks like. And then the test comes and they're all just like random lumps of mineral and you have no crystal shapes. The colors don't match up to what you want. And he was a jerk, and he'd put like, in a test with like 50 rocks, he'd put like 10 quartz in there. And so you're going through it and you're like, well, I've already had quartz, so probably this isn't quartz. And then you go to the next one and you're like, well, this can't be quartz either. And you get to the end of the test and he's like, there were like 15 quartz in there and all of y'all got them wrong. It's like, well, who does this? Why are you doing this to us? I will not do that to you. We'll have a very limited number of samples. And when we do the lab, I will have a basically like a flowchart packet, and it will ask you certain questions about the properties of a mineral, which we'll go over in a second, or we'll start to go over. And basically, it'll ask you like, what is the luster? If you think it's this luster, turn to page 3. If you think it's this luster, turn to page 4. And on page 3 and 4, it'll ask you the next question. What is the color? If it's this kind of color, if it's light, if it's dark, turn to this page. And you kind of go through it, and hopefully by the end, if you've answered all the questions correctly, it should get you to the right set of minerals, and you can choose from those from some specific details. I will obviously help you through it and kind of let you know if you've made the wrong decision here or there, and hopefully get you to the correct page at the end. But it's up to you to figure out what the actual mineral is. So I'm going to leave this on for a second so everybody can kind of see the minerals in a nice light. But we're going to go to the next page. Minerals have that definite chemical composition that some of them allow for variation. Some of them do not. But like quartz, you can see that quartz is like a yellowy brown kind of color. If you've ever been to somewhere that sells quartz, you know that they come in almost any color. There's black quartz, purple quartz, pink, red, green. They come in almost everything. Let me get the samples so they get passed around.
Everybody's hands on.
Oh, well, yeah, if you don't want to do that, you can. But I was going to be like, minerals are antibacterial, but they're not. They're not. And that being said, like in a different time and different age, there's some minerals that you gotta, this is going to sound gross, but you got to lick. If you don't know if it's salt, what's the best way to find out if it's salt? You give a nice lick. And not to call him out because he's a great guy and he jumped out there and did it. In a previous class, John Mabry licked a piece of Jurassic salt. Very old. Yeah, you would have known it was Mabry. But yeah, we got a piece of salt from the Jurassic era. And he was like, does it taste like salt? And licked it. And it does. Of course it does. It's salt. All the salts are going to taste like salt. So now that everybody's done with those, they do have a definite chemical composition. Quartz is always SiO2. To get that color change from purple to yellow to red or whatever it is, there are extra elements kind of shoved in here, but it's to such a small degree, it's not enough to alter the chemical composition. And if this were a mineralogy class, we might talk about what minerals or what elements have different colors. But in general, quartz is always just SiO2. No matter what color it is, there's not enough in it to really change the chemical formula. The composition may vary slightly if certain elements substitute for others. There are some minerals that we kind of call trash minerals, and that's not like a slight to it. It just is kind of a phrase to describe how you can kind of throw different elements in certain areas of the chemical formula, and it doesn't really matter what elements in there can be substituted in. It's still going to be that same mineral. So it's not like a slight on it. It's a trash element. Substituting elements about the same size will not change the crystalline structure of the mineral, and ideally it would be the same mineral. So here's where we get to some of the weird stuff. Is this a mineral? Why or why not? So ice, is this a mineral?
No.
So I would say no also, but let's go down it. Is it inorganic? Yeah, it's not organic. Is it a solid? Yes. Now, here's the thing. For most of the world, ice is not a solid at standard temperature and pressure on Earth. At the poles, yes, and the cold places it can be. Is ice always pure? No. And so you could argue that ice doesn't have a definite chemical composition. You could also argue that it does. It's H2O, and anything else in there is just kind of an impurity and not really part of the ice. Now, here's where I think ice might lose out, although I'm not 100% sure. I don't know that ice definitely has that definite crystalline structure, where every time you make ice, all the water molecules are locked in the same formation as every other piece of ice. I might be wrong on that, but if you Google it, I think you'll probably find pages that say yes and no. To be fair, I think the book says yes, and probably some of the web pages say yes. But I would agree with you, and I would say no. In general, when we talk about minerals, ice doesn't really come up all that often. Next, cubic zirconia, is this a mineral or not? No, because made in a lab. Yeah, man-made. If we were talking about diamonds, or a ruby, or an emerald. Which, by the way, ruby and emerald, the reason I'm having a hard time thinking of them, those aren't the mineral names. Those are the gem names. And so ruby would be corundum, I think. Maybe it's not corundum. Maybe corundum's not. But they have specific mineral names, and when you use them in jewelry, we kind of change their names. With chocolate, is chocolate a mineral? No. A, it's not always solid. B, it's organic. Chocolate is made from cacao beans. Not cocoa beans, cacao. A gold nugget, is gold a mineral? Yes, it is a native mineral. It only has one element in it, but gold is a mineral. It's formed naturally. We can reform it in a lab, but we didn't make it. We just kind of used it. Did you see the mineral name for?
Yeah, emerald or ruby, you were right, and then emerald is like beryl.
Yeah, emerald is beryl. Yeah. Which I have a hard time remembering because beryl, I don't know if it's always green. I think there can be like blue beryls and different stuff like that. Glass.
No.
Glass. Now, I think in some circumstances glass can. I might be wrong on the crystalline structure part. Glass, yes, glass in your window is man-made, not a mineral. But there are natural parts, natural places where glass is formed. So like if you've ever seen the lightning strike the beach kind of thing, that makes glass. That's made from natural processes with natural minerals. And it's probably just a lot of quartz, SiO2. That being said, I don't know that glass has a definite chemical composition. And even with a natural lightning strike kind of thing, I don't know that it has a definite chemical structure or molecular structure. So probably a no on the glass. And in fact, they talk about volcanic glass on the next slide, and it's a no for volcanic glass, definitely, and I'll talk about that. And then salt, yes, that's the halite that we saw in the picture, the nice clear squares or cubes. So that one is a definite mineral. So I hope you kind of see that on some of this stuff, it's not necessarily definite. It depends on the way that you think about it. So here's the definition for a rock. A rock is a naturally occurring, and we already talked about that with minerals, solid, which we already talked about with minerals, aggregate mass of minerals or mineral-like matter. What does aggregate mean in this way? If it's made up of minerals, an aggregate, and they kind of use this in business terms, I think. An aggregate is a collection of things. You've kind of amassed several different things and put them together. And so that's what they're talking about there. It's your collection of minerals that are combined to form a rock. Most are aggregates of several different types of minerals. They do in a second. Well, no, I went too far. Not all of them are made of different minerals. They will talk about the native minerals, which are just one single element. But they contain those individual properties. So if a mineral is hard and you put it into a rock, that rock will likely be hard. And we'll see that on the next page. Some rocks are composed of a single mineral. Their example is limestone, which we have a lot of here in Texas. If you're driving down the road and you see people's white driveways, that white rock is limestone. And almost 100% of limestone is just calcite. It's formed in deep oceans. It's also formed from a lot of organically made calcium carbonate, from shells and internal components of different marine life. Some rocks are made of non-mineral matter. We don't really consider these minerals, but they do make up rocks. So like coal is made from plant material. Obsidian and humus are glasses, or pumice are volcanic glasses. And the reason these aren't considered minerals, they cool so quickly that your atoms don't have a chance to form that crystalline structure. It's basically just this random mix of different minerals and different atoms. And it doesn't really get a standard chemical formula or a standard crystalline structure. When you look at it through a microscope, it's just a random mess. So here's your granite. What's the, not number one, but what's a very common domestic use for granite today? Countertops. I will say that note that your countertop might be granite. Granite is also now an industry term used to describe any hard rock countertop. And so easily your countertop could be diorite or a metamorphic rock or something that is very much not granite to a geologist, but they just still call it a granite countertop. That's the term we use. That being said, a lot of countertops are granite. They have this exact look to them. And we use granite because it's hard. If I have a rock countertop and I like drop my pot on it, I don't want the pot to break my counter. If I drop a glass on it, I don't want my glass to break, but the counter is more expensive than the glass. So, if the glass breaks on the counter, that's okay. So what makes up granite? We have 3 different minerals generally. There could be others in there. It just depends on what kind of granite you have. But quartz, hornblende, and feldspar. And if you look up these minerals individually, they're all individually hard. Quartz has a hardness of 7 on the Mohs scale, which is pretty tough. Hornblende is like a 6, 6.5. Feldspar, I think, is like maybe a 6.5 to a 7.5. And so all of these are hard minerals. So when you drop something, it's not going to chip or break. If for some reason you're a maniac and you're not cutting on like a cutting board, and your knife goes across the granite countertop, it's not going to leave like a deep gouge. You could scratch it, but it's not gonna be too bad. Are you laughing because you just cut on your granite countertop? Oh well, sometimes you just don't want to dirty an entire. You just got to cut a lime or something.
I was watching Selling Sunset. You know that?
Yeah.
And they were talking about, it's like real estate. And one of the houses in the kitchen, they had like Calcutta marble on.
Oh yeah.
And they were like $40,000 a slab.
Yeah, marble's real expensive.
Yeah, I know. I was like, who needs that much money in their kitchen?
If you got a lot of money to burn, I mean, there's some people that they'll never run out of money ever. I'm not gonna get into money talk. We're gonna keep going. Yeah, that's one of the reasons we use it. We use it for building materials. We use granite for all sorts of things because it's hard. It has good structure. As long as you get a good piece that doesn't have like a fault running through it or a weakness, it's going to last for a really, really long time. It's not easily weathered. So they asked down here, what is the relationship between atoms, minerals, and rocks? It's like a building hierarchy. Atoms obviously make up everything in the not just the world, but the universe. So atoms are what we use to build our minerals. Well, we don't use them, but atoms are what build minerals, and minerals are what build rocks. And so it's kind of this hierarchy of size there. And that's what they say here. All atoms, excluding hydrogen and helium, formed inside massive stars by nuclear fusion. So remember, I went over that in the last chapter. After the Big Bang, there were really only 2 elements, hydrogen and helium. Everything else had to be smashed together. You put the nucleuses together, and the more nucleuses you smash together, the bigger your elements get. And so that happens inside stars. And then eventually the star goes supernova, spreads all those elements out in a big gas cloud. And if they condense in the right way, you have a nice planet like Earth that has all these wonderful different elements and different chemicals in it. An atom is the smallest particle that cannot be chemically split. We have figured out ways to physically split atoms in particle colliders and in atomic bombs. Although some atomic bombs, you're not splitting atoms, you're actually combining them and releasing energy. So it depends on exactly what type of weapon you're looking at. But atoms contain even smaller particles, your protons, neutrons, electrons. And if you get down into particle physics, like muons and gluons and leptons and quarks and all sorts of other weird stuff. We're going to go through this kind of quick because y'all have all taken chemistry, and this is just like a refresher. Every element has a specific number of protons, and so nickel will always have 29. Most elements don't change that often. You can have an element switch to a different element through radioactive processes, which we will talk about in this class. But in general, like an atom of silver or gold has always been silver or gold. It will never, ever change. It has the same number of protons. It's nice and stable. Most minerals are chemical compounds, 2 or more elements joined together. Some of them are called native minerals. They only have 1 element. And most of those, sulfur is a rare example or a rare exception. Most of those are metals. So like copper, gold, platinum, silver, iron, all the different metals that we use for all sorts of different purposes. They are both an element and a mineral. Sulfur is a different one. It is a single element. It's a native mineral and it's not metallic. So that's one of the rare ones. They go through different chemical bonds, which we're not going to talk about very much. But they mention ionic bonds where you're sharing electrons, Covalent bonds, well, no, ionic bonds, you have electrons transfer, and they're stuck together because of their charges. So you have a positive charge and a negative charge, and they attract to each other. Covalent bonds are where you're sharing electrons. Metallic bonds, they have the sea of electron model, where the electrons can move freely from atom to atom. It kind of helps hold them together, but it also gives them their nice properties of being malleable. We can stretch them, we can bend them. Electricity passes through them very well, and so that's a very good thing. For their example, for an ionic bond is salt, which we already talked about as a mineral. We already showed. Your sodium loses an electron and becomes positive. Your chlorine gains an electron, becomes negative, and that negative and positive attraction is what holds them together in these very specific formations. Covalent bonds, yeah, metallic bonds. Remember that because of the metallic bonds, we have electrical conductivity, which is great for electronics. They can be bent and shaped and stretch out into thin wires, and some of them even have other unique properties. Okay, and we're going to leave off because y'all are getting ready, so it must be time to go soon. Yes. We're going to leave off with the properties. So tomorrow we're going to start to talk about the properties, which is how we identify minerals. So we have things like luster, which is how they look to you, how they shine light off. Color, which is great, but not really super helpful. Streak, which is the powder that it leaves behind. Crystal shape, so you can see that several different crystal shapes of pyrite here, and some other examples here. Tenacity, which we won't really talk about because I never really used very much. It's more of an engineering term. Hardness, which is important. And then cleavage and fracture, which are all, it's like two sides of the same coin, but we will talk about cleavage and fracture. I don't need y'all laughing every time we say cleavage either. Yeah, that's it for today. Remember, homework is due today before midnight. The test will be tomorrow in class, or if you're online, the test will be whenever you happen to take it, but it will be 45 minutes. And there's no lockdown browser, but by the time we take another test, there will be. So everybody have a nice day.